Hey folks, going to look at graphing some polar curves today. Before we do that, we're going to do a little bit of review from what we talked about last class period, going between polar and Cartesian form, both for simple coordinates and also for equations. So go ahead and work through these 5 problems real quick, and then I will show you my solutions to those problems. So, first one, here we go. We are dealing with a polar coordinate right here, r comma theta, and we want to take this polar coordinate and convert it into a Cartesian coordinate, x comma y. To do that is fairly straightforward. We need to remember 2 simple formulas. We need to remember that x is equivalent to r times the cosine of theta. That came from our last lesson, just looking at a triangle with x, y, theta, and then the hypotenuse labeled as r. So x equals r cosine theta, and similarly, y equals r sine theta. So we just need to use these 2 equations to go from this polar point to a Cartesian point. So our radius is 4, our angle is 3 pi over 2. So if we're writing the coordinates of this point, x is going to be our radius 4 times the cosine of that angle, 3 pi over 2, and y is going to be the same radius r times the sine of that same angle. So all we need to do is simplify these pieces, and so we're going to need to think about the unit circle. So where's 3 pi over 2? Well, that is right there. What's the value of cosine there? Well, cosine there is 0. Cosine is an x value on the unit circle, and so the x coordinate there has to be 0. What is the y value there? Well, y has a value of negative 4, or rather sine has a value of, what am I even saying? Sine has a value of negative 1 at 3 pi over 2. Sine of 3 pi over 2 is negative 1, so 4 times negative 1 is negative 4. And we get our rectangular coordinate just like that, 0, comma, negative 4. So now let's go the opposite direction. Let's take this x, y ordered pair, Cartesian coordinate, and let's turn it into an r, comma, theta polar coordinate. To do that, we need to remember a couple things. We need to remember that x squared plus y squared equals r squared. And that's just coming from the triangle with adjacent side of x, an opposite side of y, and a hypotenuse of r. And so we can directly substitute these pieces in and say negative 2 times the square root of 3 squared plus 2 squared equals our r squared. And so let's go ahead and square this stuff. When you're squaring negative 2 times the square root of 3, that's like squaring each piece and multiplying them together. So negative 2 squared is 4. Square root of 3 squared is 3, and so we get 4 times 3 is 12, plus 2 squared is 4 equals r squared. So 12 plus 4 is 16 equal to our r squared, and so we get that r equals 4. So now we need to find our theta, and to do that we can recall that theta is equivalent to the inverse tangent of y over x. And so let's plug those pieces in to our inverse tangent function and see what we get. Well, y is 2 over x is negative 2 times the square root of 3. So we get this right there, which we can simplify a little bit before we start playing with it and thinking about it. So let's simplify this piece. 2 over 2 reduces down, and we're left with 1 over the negative square root of 3 right there, which again we can actually simplify further by rationalizing that denominator, the tan inverse of negative root 3 over 3. Remember, to rationalize that denominator, you are multiplying by the square root of 3 in the denominator and in the numerator. 1 times the square root of 3 gives us that new numerator of square root of 3. Square root of 3 times the square root of 3 gives us that new denominator of 3, and it is all still negative. So, to answer this question, to determine that theta value, we need to use our knowledge of the unit circle. Now, inverse tangent is going to tell us what our angle is. So essentially what it's asking is, on the unit circle, what theta what angle will give you a slope, because remember tangent on the unit circle should be thought of as slope, what angle will give you a slope of the square root of 3 over 3? And I remember a couple things. I remember that if I'm looking at these 2 points right there, slope is 0. If I'm looking at these 2 points, slope is undefined. If I'm looking at any of these pi over 4 values, the slope is either 1 or negative 1. So the only values I really need to look at are either these pi over 6 lines or the pi over 3 lines. Now, of those two values, I remember that one has a tangent value of the square root of 3, and the other has a tangent value of the square root of 3 over 3. That's just something I remember. You can also just use the xy points from your knowledge of the unit circle, but you should get there either way. Now, of these two numbers, remembering that they're representing the slope, which of these two numbers is bigger? Well, the square root of 3 has to be bigger because the other number is the square root of 3 divided by 3. And so the square root of 3 is going to correspond to that pi over 3 angle, and the square root of 3 over 3 is going to correspond to those pi over 6 angles, which means if the slope we want is negative root 3 over 3, we have to be looking at one of these negative slopes right there. So we're looking at either that angle right there or that angle right there. This angle, 11 pi over 6, and this angle over here is going to be 5 pi over 6. Again, just coming from what we've done with the unit circle already. So one of those is my answer. How do I know which one? Well, you got to look at that original point. Notice x is negative and y is positive. If x is negative and y is positive, which quadrant are you in? Well, you are in the second quadrant right here. And so our angle has to be 5 pi over 6. So we get our point 4, 5 pi over 6. And if you take this the other direction, you should hopefully end up with those same x, y values as we started with. So there you have it. Let's move on to our next step. So here we have an equation in Cartesian form. X squared plus y squared equals 25. You should recognize that as a circle with a radius of 5. And so now we're just answering the question, well, how do we write the equation of a circle centered at the origin with a radius of 5, not in Cartesian form, because that's what we have, but in polar form? Well, it couldn't actually be any easier. It's just r equals 5. Which is why you always hear me referring to r as the radius. That's how I choose to think about it. But what's another way we could look at this? Well, we used previously that x squared plus y squared equals r squared. And look, we have x squared plus y squared right there, so we can just replace that with r squared. So 25 equals r squared, and if 25 equals r squared, then r equals 5. You could also write r equals negative 5, but let's just use the positive one there. Next equation, y equals 10. Again, we just need to directly substitute in what we know. And what do we know about y? Well, we know that y is equivalent to r times the sine of theta. And so, if I have r sine theta equals 10, I just want to solve that for r. And so then r equals 10 over sine of theta, which we could simplify a little farther and say that r equals 10 times the cosecant of theta. So notice what just happened. We took the equation of a horizontal line, and to write that same horizontal line in polar form, we wrote it as r equals 10, the original y value we wanted, times the cosecant of theta. So if I wanted a y equals 5 line, I think we could probably write that as r equals 5 times cosecant of theta. Well, what if I wanted a line that said x equals 13, a vertical line? Well, maybe you can prove this, but my guess is we would have r equals 13 times the secant of theta. So hopefully you're noticing some patterns here, and let's go ahead and look at that last problem. So 2x minus 3y plus 5 equals 0. Again, just plug in what we know and solve for r. We know that x equals r times the cosine of theta. We know that y equals r times the sine of theta. So plug those in. 2 times, instead of x, we're writing r cosine theta, minus 3 times, instead of y, we're writing r sine theta, And instead of adding 5, I'm going to subtract that over to the other side right there. Now what can we do on the left? Well, both of these terms have an r, so I can factor out that r, and I'm left with 2 cosine theta minus 3 sine theta. Use brackets since that's what I used before, equals that negative 5. And I want to get r by itself, so I need to divide by everything in those brackets. And so r equals negative 5 divided by 2 cosine theta minus 3 sine theta. And we are finished with that. So let's then move on to our main objectives for the day. We want to graph a polar curve. And now we're going to look at how we do that. So before we go ahead and graph an actual polar curve, what we're going to do is graph this Cartesian equation first, this trig function. It's a cosine function. So how do we graph this? Well, let's look at a couple pieces. Let's think about what does that 3 do to our function? Well, we should all know by this point that that 3 is going to shift my function up 3. So what I'm going to do is I'm going to go 1, 2, 3, label that 3. I'm going to go ahead and dash in an axis of symmetry that will run down the middle of this cosine graph. And then I'm going to look at this 5 right here and ask myself, what does that do? Well, that changes my amplitude. It makes it from an amplitude of 1 to an amplitude of 5, which means from that axis of symmetry, I'm going to go up 5. So 1, 2, 3, 4, 5 puts me at a maximum of 8. And I'm also going to go down 5. So 1, 2, 3, 4, 5 puts me at a minimum of negative 2. The only other thing you really need to think about when graphing a basic trig function like this is, have we modified our period? No, we have not. There is no coefficient in front of that variable inside of the cosine function, which means our period will be a normal to pi. And so let's now graph this. Split up 2 pi right there. Let's go ahead and put halfway a pi, halfway again a pi over 2, and between these 2 points a 3 pi over 2. All right, now we're graphing a cosine function which starts at its maximum value. So our first point here is going to be up right there, and then we're going to run through our cycle as we normally do. Each tick mark, we're going through a quarter of our cycle, and so we're bouncing between either the minimum, the maximum, or that middle value. Once we have those points, we should be able to sketch that graph in. Whoa, kind of ugly, but good enough. It will give us a pretty good idea as to what is going on. So that is a first step in our process for graphing these polar curves. Graph the corresponding rectangular equation, the Cartesian equation, the normal trig function like we've done all the time. Now, instead of thinking of this and as y and x, let's think of the vertical axis not as y, but let's think of that as r right there. So I'm going to label this as r. So now you need to remember that all of these vertical values that we're looking at, the vertical component that is making this graph, those are all representing our r values. And the horizontal components here, instead of x, let's go ahead and think of that as a theta. So now we're dealing with r and theta, and I need to make a huge distinction here. I am in no way saying that this is the graph of a polar curve. No, absolutely not. We graph this like we graph normal rectangular equations. What I'm going to do is I'm going to use this graph essentially as a data table. So I'm going to use this to help me find key points on my polar curve. And let's take a look at how to do that now. So now let's go ahead and graph this as a polar curve. And to do so, let's go ahead and almost pretend like we're drawing a unit circle. Let's draw some axes here. And let's label what we know. Let's label 0. Let's label pi over 2. Let's label pi, 3 pi over 2. And then also go ahead and remind ourselves that one full revolution gets us back to 2 pi. Now, I'm going to increase the detail here by drawing in my pi over 4 lines. So go ahead and dash in these pi over 4 lines. I'm just choosing to draw them as dashed lines. It does not make any difference here. So 0 to pi over 2, halfway in the middle, we get pi over 4, and then we have 3 pi over 4, and then we have 5 pi, 5 pi over 4, and finally 7 pi over 4. And now I'm going to take this graph right here that we came up with on the previous page, and I'm going to turn it into a polar curve. And to do so, like I said, I'm going to think of this almost as a data table. So if I'm looking at these as a set of points, r, comma, theta, I'm going to go to my first theta value, and I'm going to get my radius. So that point right there is telling me that I have a corresponding polar coordinate, 8, 0, and remember it's r, theta. So what that's saying is when I'm at the theta value of 0, so when I'm out on this line increasing to the right there along that angle line, I have a radius of 8. So I'm going to plop 8 tick marks on there, and I'm going to go ahead and put my point there. So there is my first polar point. And again, I used the Cartesian graph as a data table to get there. I knew that the radius was 8 when the angle was 0. So you have to keep in mind that we're always going to be going out from the pole. That middle point right there in the middle, kind of equivalent to the origin in a way, is called the pole. And you're always going out a distance in the direction of your angle. So the angle 0 takes me out to the right, and I went out a distance of 8. Well, just like over here, we graphed this cosine function using key points. We're going to graph this polar function, this polar curve using key points as well. So let's look at this next easy point that we can use that is corresponding to the polar coordinate. Notice your radius is now 3. Remember, the vertical pieces are our radius values, and the angle is pi over 2. So I'm going to plot my next polar point. I see that pi over 2 is straight up from the pole right there. And how far am I going? Well, I'm going 3. So I'm going to go 3 tick marks. 1, 2, 3. And I'm doing this by hand, so I'm trying to keep my scale as consistent as possible. But I get a point right there. I get my second point. So here's my first point. Here's my second point that I found. And I need to somehow get from here to there. But what does it look like? It probably doesn't look like that. It probably doesn't look like that. So what does it look like? Well, let's analyze our rectangular graph and think about what's happening to each of these radius values here. So notice what's happening between this point and that point. The vertical component is getting smaller, which means my radius is decreasing from 0 to pi over 2. Now, to make it a little easier to see this shape of the graph, let's go ahead and go halfway in between, and let's look at the point pi over 4. This will hopefully give us a better idea of where our graph should be between 0 and pi over 2. So here we have the point happening when our angle is pi over 4, and let's figure out what our radius is. And to do so, we're just going to use this equation. We're going to plug in our angle of pi over 4 and see what r value we get. So let's do that. R equals our 3 plus 5 times the cosine of pi over 4, which we can simplify a little bit by hand. R equals 3 plus 5 times, what's the cosine of pi over 4? Well, it is the square root of 2 over 2. And if you calculate that out, you get roughly 6.5. And so we're going to use that as an approximate value there. And again, it's giving us a point. It's saying that at this point, our radius is roughly 6.5 when the angle is pi over 4. And so I'm going to translate that over here onto my polar graph. Well, there's my angle pi over 4 right there. Let's go ahead and give ourselves some tick marks. And what were those tick marks? 1, 2, 3, 4, 5, 6, 7, and we were at 6.5, so we are right about there. So that gives us a much better idea of what this graph is doing, because I see from this point, I'm not going straight there, I'm not going like that, I have to curve up to that point and then come back down, so I'm kind of getting like a little bubble. So maybe at this point we should go ahead and fill that in. So I'm just going to draw a curve there that seems to fit this shape. Remember, we're dealing with a polar curve. Everything is going to be nice and smooth and pretty. And let's see what happens from here on out. What happens at 3 pi over 4? Or next easy point, what happens at pi? So, same pattern. Here's our next easy point at pi. It's giving us a polar coordinate. It's saying that the radius is -2 at the angle pi, which is a little interesting here because now we're going to be forced to think about this in a way that's a little different than you've thought about coordinates before. We're dealing with a negative r value, which means normally the angle of pi is going out this direction. As the r increases, we'd move farther and farther out along that angle pi. But since our radius is negative, we actually have to go the opposite direction, which means along that angle pi, the radius is -2. We have to go 2 in the opposite direction, putting us right there, which is strange. But again, I need to figure out how do I get from my last point to that point. So again, let's check our graph right here. So let's go between pi over 2 and pi. Let's check at 3 pi over 4. And let's think about what we know about the symmetry of this graph. Since I'm moving the same distance from that midpoint along my axis, think about this vertical displacement from that point up to that point. We went from the line 3 to 6.5, so we went up about 3.5. Now similarly, if I want to go from that, again, midpoint down to where this is, I need to go down 3.5. And so I can just say 3 minus 3.5 gives me roughly -0.5. And so at this angle of 3 pi over 4, I'm actually down at a value of -0.5, which means if I put tick marks here, -0.5 is going to be about there. And so this graph, again, has to go smoothly from this point right there down to that point right there. And there's one other important piece on this graph over here that we should make note of. We should notice that we have a 0 right there. We have a spot where the radius is 0. Now think about where on here a point would correspond to a radius of 0. Well, it have to happen right at the pole. We don't go any distance out. So I'm going to try and continue this curve as smoothly as I can, and it's got to look something like that. And then if I continue on to that next point that I found, I hit it right there. All right. Now at this point, think about where we are on this graph. We have gone halfway through the period. And at this point, everything we do is going to be repeated in reverse. If you can think about our next nice point is happening at 3 pi over 2, where our radius again is 3. And so I can picture this point over here at 3 pi over 2. My radius is 3, so I got 1, 2, 3. Notice it is a perfect mirror of this point right up there. And I could say, well, hey, that's not enough information, so I could look over here again, and I could say, let's go halfway in between at 5 pi over 4. We'll notice that that point and that point will have the same y values, or r values, you should say, so that would be a -0.5 again. So just like I got this little awkward point right there, I'm going to get another little awkward point right there. And just like we crossed the pole right there, we're going to cross the pole again right there. So this graph is going to be a perfect mirror image. So I'm going to curve out like that, and then I'm going to finish up in the same manner. Halfway between there, I get that same r value again, which was 6.5, and then I'm going to finish off right where I started with a radius of 8. And this is going to be perfectly flipped down. So let's finish that up. And I end up with a Limacon. That is how I pronounce it. I'm not sure how you want to pronounce it. I've heard people say it a lot of different ways. I think Limacon is the French pronunciation, but that's what that graph is. This is a Limacon with an inner loop. You can spell it like this. You'll see it with a little squiggly thing on the C. I don't know what that's called, but there you have it. And let's remember what this equation was. This equation was R equals 3 plus 5 cosine theta. And I want to point a couple important things out to you. Now, look at this 3 right here, and look at that 3 and that 3. And look at this 5 right here, and look at 3 plus 5, giving us that 8. And look at 5 minus 3, giving us that 2. There are very important connections here to be made. You have a couple problems to do for homework, and you should hopefully continue to strengthen those connections. But we get this perfectly symmetrical curve looking like that, and we have graphed a polar curve. So let's finish just by thinking about what we just said. Given the graph we just found, 3 plus 5 cosine of theta, how would it look differently if we did 5 plus 3 cosine theta? Well, remember what that 3 did. That gave us that 3 and that 3 right there. So if I change that value to a 5, that means I'm going to get 1, 2, 3, 4, 5, a point up there, and 1, 2, 3, 4, 5, a point down there. And what did that 5 do with that 3? Well, they added together to give us that piece, and they subtracted to give us that 2. And so we can do the same thing. We can say the 5 plus 3 is going to give us a point there again, or rather I should say the 3 plus 5, and then the 3 minus 5 is going to give us a point out here at that negative 2, which means we're not going to end up with an inner loop this time. It's going to end up looking something like this, with a little dimple. Wow, that was pretty bad. Let's try that again. Whoop, whoop, whoop. Like that. So just by changing that little bit, we've significantly changed what this shape looks like. So, play around, see what you can do.